This is a single stage batch distillation for a binary mixture of methanol and water. We're going to assume ideal solution to make calculations easier. And the question is, how much distillate will we collect when the concentration is 90%? We want the concentration not to go below 90% in the distillate. And then how many moles will be left in the still at that point, and what will be the composition of the methanol in the still. And I've given the Antoine's equations for the two components. And let's look at the notation. So what we're starting out with is in the still, we'll use the term W for number of moles initially, and that's 75. And the mole fraction, we're going to use the notation of 1 for methanol and 2 for water. But all the equations I'm going to write down are going to be in terms of mole fraction of methanol. In order to not make the notation too complicated, I won't write the subscript 1 in general in these equations. So XW means the mole fraction in this still. So this is the still, and this is the distillate. That mole fraction, we start out at 0.82. The amount of distillate, we'll use the term D. So this is D moles. And the mole fraction above the liquid in the still, we'll call YD. So YD is in equilibrium with XW. Then we start out, of course, there's no distillate at the beginning. And then as we distill, the level here goes down. Level here goes up. We want to calculate what's the value of D, where XD is 0.90. Now notice, remember, YD is the mole fraction, and so YD equals XD when we have a single stage batch distillation that we're looking at here. So the equations that govern this behavior, where we have to account for the fact that the mole fraction XW and YD, and therefore XD, change with time. The mass balances are derived in a separate screencast, and what we want to look at here is how we go about dealing with this particular problem using those equations. And so the important equation is the Rayleigh equation that we derive from the mass balance. And that says the integral from XW0 to XW. So when we stop, W is going to be the number of moles that are left. XW will be the mole fraction. And so dxW over YD minus XW. And that's equal to the log of number of moles when we stop, number of moles we started with. Now the important thing, to be able to solve this equation, we have to relate YD and XW, and this we do by relating vapor-liquid equilibrium expression. And what we're going to use, because it says ideal solution, we're going to use Raoult's law. So note for component 2 for water, I use the subscript 2. I use the subscript 1 here for the saturated pressure. I could certainly put a 1 for XW and YD, but to make things not too complicated, I won't do that. Now, what we're going to do is rearrange these equations, and what we end up with that's of particular use for this particular problem, XW is related to the total pressure and the saturation pressures. So P1 sat minus P2 sat. And YD then is going to be equal to XW P1 sat over P. So these are the two equations that we're going to use in our solutions to account for Raoult's law. We're going to solve the Rayleigh equation. I'm going to substitute XW and YD into the Rayleigh equation. So the thing you're going to see right away is that the XW and YD depend on saturation pressures, which depend on temperature. And so it's not an analytical solution. We're going to have to solve this numerically. So let's write down the equations for the saturation pressure. So we have all the equations we need to solve together. So these two equations are Antoine's equation we need to substitute these into here, and then substitute these equations into here and do the integration. This is what we're going to do numerically. Going to do that using Excel, and Excel then allows us to calculate W. And then once we have W, so let's look at what else we need to calculate. We need to calculate the amount of distillate. Well, that's just how much we started with in the still minus how much is left. That's number of moles. The objective is to calculate the point where XD average, meaning all that we've collected rather than taking samples and then collecting more, all the distillate. We're aiming for that to be 0.90, and that's equal to how many moles we start with in the still, so the moles times the mole fraction, how many moles of methanol we start with, minus how many moles of methanol we end up with, total number of moles times the mole fraction, divided by this value D, number of moles of distillate. So that tells us when we stop solving the problem, basically. So we're going to solve this using a spreadsheet. Here's the solution. We have 12.5 moles left. Mole fraction, of course, of methanol is decreased significantly to 0.42, let's say. And we have 62.5 moles of the distillate. And remember the problem, the mole fraction, the distillate, 0.90 when we finished. So we'll, in a separate screencast, look at the spreadsheet that does this calculation.